There is a fairly large group of physicists who believe that time is a statistical phenomenon like temperature and pressure. This is because time appears in a similar place in quantum statistics that temperature does in ordinary molecular statistics. The concept is that time is emergent. If something is emergent, that means that it emerges from the sum of many parts, but you won't find it in any individual part. The image of Van Gogh in this pointillist self-portrait is emergent. No brushstroke contains the image, but together they construct a picture that is only rendered in our own minds. Temperature is similar in that individual molecules have none. They have energy, but temperature is an average of the kinetic energy of many molecules taken together. Recent research published in Physical Review Letters points to time being emergent from the quantum interaction between systems and their environment. Starting from a static quantum state, they were able to derive the time-dependent Schrödinger equation, which suggests that time can emerge from states where time is not there at all. The parameter that becomes time in this derivation also becomes temperature if it is an imaginary number, which points to a mathematical connection between the two. By partitioning their global system into a system and a clock, as well as their interaction, they show how the entanglement between the system and the clock creates time. How can this be? In the paper, the authors, Gemschein and Rost, show how time emerges from a set of projections. A projection is a term for when you take a mathematical object in some number of dimensions and project it onto a space with a lower number of dimensions. Just as a bright light shining against your three-dimensional hands produces a bunny on a wall, a projection takes away information but also adds some. In this way, it removes the three-dimensional information of your hands while adding information about the light. Thus, when a global state, representing the world of both system and clock but static with no concept of time, is projected against an environmental state representing a clock, you get a system state that is the global state evolving in time. While the global state obeys certain symmetries that are completely independent of any parameters, the projected state obeys symmetries that are controlled by the parameter representing time, the tick of the ticking clock. This parameter is present in the clock. Thus, the projected state, the result of the interaction between the global timeless state and the clock, gains time. The parameter that we call time can be given physical meaning now by relating it to motion. That is, the movement of a particle in the projected state as the parameter changes implies a physical definition of time. The interaction between the global state and the clock is important because, without it, you could define separate time parameters in the projected state and the clock. Essentially, in a non-interacting system, the clock and system would not have to move at the same rate or mean the same things. Interaction forces them together. This may be why all parts of the universe share the same clock more or less, and why quantum particles, when we observe them, appear to obey time with the same arrow that the rest of the universe follows, for the most part. Is pinning time down as simple as proposing a quantum model by which it emerges from a static quantum state? At best, it tells us how one can go from a static state to one that implies some kind of forward evolution. Yet this model tells us nothing about why time has an arrow that travels in one direction. Nor does it explain our own perception of time as flowing from past to future. In general relativity, Einstein's theory, time is defined by gravity, which explains why one observer can have a different measure of time compared to another. This is why the Global Positioning System, GPS, that we all use every day, has to account for the different rate at which time flows up in orbit than down on Earth. Without that correction, positions would be miles off. The Einstein field equation, the equation of motion of general relativity, can be written as evolution equations in time, or at least some parameter which we name t and give the name time to. The physical interpretation of this parameter, however, bears little resemblance to time in non-relativistic theory, such as that of Isaac Newton. In Newton's view, there is absolute time that reigns everywhere, and all clocks measure it. Thus, this time t, in his theory, is something that we can observe. It is an observable, in physics parlance. In Einstein's view, however, time t is not observable. Only our proper time, which is sometimes given the coordinate name s, is. When you read off the hands or digits of a clock, this is what you are observing. The time where you are, not global time t. You see, t is just a label for a coordinate like x, y, or z for a spatial coordinate. It has no intrinsic meaning. In other words, it isn't measurable except in an artificial way. This is both the blessing and the curse of general relativity, called general covariance. It is a blessing in that we understand now that coordinate transformations have no physical meaning. They are mathematical, and anything that is observable must be invariant under such transformations. It is a curse because it removes the inherent measurability of time and space that we are able to maintain in non-relativistic and even special relativity, relativity without gravity. Einstein himself found this very puzzling, and it took him many years to realize that general covariance is not a real symmetry of general relativity. In fact, it was an artificial symmetry of coordinate systems that later mathematicians would remove completely from GR with the theory of differential forms, a coordinate-free way of understanding the theory. Differential forms are like measuring devices, a mathematical gadget for giving you information about something. Think of a measuring tape. You provide a measuring tape with some length, say a 2x4, and it spits out a single number. Differential forms are similar in this regard, and come in various forms, depending on what they take in and what they produce. A 1 form, for example, takes in a vector, some pointing direction, and gives you a number in much the same way a measuring tape gives you a number from a one-dimensional length. A 2 form takes 2 vectors and gives you a number. Think of this as something used to measure the area of a rectangular room. Each side of the room is like a vector, and the 2 form is something that measures the room's area by taking in those 2 sides. A 3 form takes in 3 vectors, like measuring the cubic space of a room and so on. You can also have 0 forms, which are just numbers. The beauty of differential forms is that they don't operate in coordinate systems, so you never have to worry about whether some conclusion you are drawing is coordinate dependent. This is important because coordinate dependence is often subtle and hard to detect. For example, some warp drive theories that travel faster than light have made the rounds in the news, only for others to argue that those solutions are coordinate dependent. A coordinate dependent conclusion is not real. It is an artificial observable. When you look at general relativity using differential forms, you see that time as a global parameter does not exist. All you have are local times. The only reason you can understand time passing somewhere else is that something traversed the space between you, such as light. You can, for example, receive a signal from a distant clock that gives you its time and compare it with your clock. You can look at how the distant clock runs slower or faster than your own clock based on its velocity and gravitational field, in the same way we do with GPS satellites' onboard atomic clocks. So you might conclude from this that you should be able to define, at every point in space-time, a clock, and that all these clocks taken together define some global time, maybe not one clock to rule them all, as in Newtonian theory, but a multi-clock theory. But you would be wrong. The reason you would be wrong is that observers at the precise same location, even if they experience the same gravitational field as each other, may be traveling at different velocities, in which case their clocks will run at different speeds. Even worse, observers at the same location could be undergoing different accelerations, which, because acceleration is indistinguishable from a gravitational field, would argue that they have different gravitational fields. While you could restrict your clocks to only observers in freefall, which is an objectively measurable condition that would exclude every clock on Earth, since only clocks in orbit are in freefall for any appreciable length of time. Thus, you can't define a universal global time coordinate using just local clocks. You must define a coordinate system that specifies how fast each local clock is running, and in which direction, and what the gravitational field is, including accelerations. Quantum mechanics, meanwhile, sweeps away all these problems, and presents time as Isaac Newton did, an external tick that keeps everything going forward. In fact, time isn't even an observable in quantum physics. It's literally just a number. Meanwhile, positions are treated as infinite-dimensional vectors in a mathematical space called a Hilbert space. This is why quantum theory and gravity are irreconcilable. In fact, the reason we have no theory of quantum gravity is primarily because we have two fundamentally opposed theories of time, one where time is purely a local phenomenon defined by clocks and observer state, and one where time is absolute and external. And even in the case where we try to derive time from a timeless quantum state, the time we derive is that absolute external time. Despite being absolute, however, quantum mechanics plays games with time that would make Isaac Newton's head spin. Take the Hartman effect, discovered in 1962 by Thomas Hartman. In quantum mechanics, particles can tunnel through barriers, meaning that they can travel through seemingly impenetrable walls and appear on the other side like quantum David Copperfields. Hartman found that when particles do this, the time they take to pass through the barrier is unrelated to the thickness of the barrier. This means that a particle could travel through a piece of paper and 1,000 kilometers of steel in the same amount of time. Even the speed of light is no barrier. It's as if the particle disappears from one part of the universe and reappears somewhere else. This is because particles in quantum physics are not represented as points as in Newtonian theory but as wave packets. These packets, when striking a barrier, will tend to split with part bouncing off and part passing through. But that wave packet doesn't behave like a physical wave when passing through the barrier, whereas in free space, it is more wave-like. Physicists actually disagree on what is going on here, even though the effect has been verified experimentally many times. Some say that the particle is traveling faster than light and violates causality. Others say this is a misinterpretation of the time to traverse the barrier. The question revolves around the definition of certain terms, such as what constitutes arrival time, and whether group delay in tunneling is a correct definition of transit time. Group delay is a term you often hear in signal processing where it refers to the negative of the change in phase. So if you see the peak of the wave above, group delay is the amount of time it takes for the peak to transit from one point to another. Group delay, even in classical signals, can appear to violate causality because you have outputs that appear to precede inputs. But this violation is an illusion. You can build a circuit where a signal's peak appears at the output before it enters the input of the circuit. What is actually happening is more a kind of copying where the circuit is copying the input's features, so it only appears that the output happens before the input. Could the same be happening in the Hartman effect? Is the barrier causing the wave packet to be copied rather than the wave actually traversing it? As one paper argues, it is not even clear whether the tunneling particles are actually going through the potential barrier or not. Quantum physics has more problems with time than that. One of its early pioneers, Wolfgang Pauli, argued that it was impossible for time to be considered a dynamical variable, meaning an observable in its own right, in quantum theory. This is because in quantum theory, the Hamiltonian, which is an operator that represents energy or energy states, generates time translations. What does that mean? It means that quantum theory contains a kind of machine called a Hamiltonian. The job of this machine is to move a quantum state from one time to the next, kind of like a 3D printer making a figurine from the bottom up. In classical physics, the Hamiltonian is just a function that represents a number, energy, but in quantum physics it represents a spectrum of energies. We call this an operator since it operates on quantum states, which themselves are these infinite-dimensional vectors in Hilbert spaces. Give a Hamiltonian a quantum state, and it gives you a new one at a later time. Since the Hamiltonian is an energy operator that generates time translations, the corresponding operator for time must be a time operator that generates energy translations. Such an operator must be related to the Hamiltonian in such a way that we would expect time to have the same properties as energy in quantum theory. That means that, for example, since energy only has integer values in some systems, such as the quantum harmonic oscillator, time should only have integer values sometimes. If energy has a smallest value, then time must have a smallest value, and so on. This goes against our understanding of how time works, at least in physics, but perhaps this is just because we are using classical intuition to restrict what quantum time can be. The proposal at the beginning of this article, defining time by some quantum clock, is one attempt to get around Pauli's proposal. But another is to argue that we can make the Hamiltonian have the properties that time normally has and vice versa. For example, some systems in quantum electromagnetism allow the construction of Hamiltonians that have no smallest energy value. Hence, these allow you to move energy up and down an infinite ladder, much the same way we imagine time working. I would argue that since the universe has a beginning, however, perhaps the idea of time being infinitely negative just isn't something that is observable anyway. Others have shown that the equations for electrons and quarks can be modified to make time have integer values. This means that time doesn't move continuously from one moment to the next, but jumps from moment to moment like a digital clock. Such efforts are valuable in that we are learning how to reconcile time not only with quantum theory itself but also eventually with quantum gravity. One mystery is what happens to time when we try to turn general relativity into a quantum theory and find that time disappears altogether. Derived in the 1970s, the Wheeler-DeWitt equation is named for John A. Wheeler and Bryce DeWitt. Both are known for a number of things, particularly their very different interpretations of quantum mechanics. Wheeler promoted an anti-realist interpretation where observers create reality by observing it, while Bryce DeWitt is well known for the many worlds interpretation of quantum theory, which he promoted as the correct way to understand Everett's 1950s paper on the topic. In any case, when it came to understanding how to quantize gravity, the Wheeler-DeWitt equation was a natural way of taking the Hamiltonian of general relativity, turning it into an operator, and applying it to the quantum state of the universe. Although this equation is ill-defined, since it is famously non-renormalizable, meaning it produces infinities all over the place when you try to calculate things with it, it does have one noticeable feature. It lacks any sort of time evolution of the universe. Instead, in the place where time evolution should be in such an equation, there is a big, fat zero. This means that from a quantum perspective, the universe does not appear to evolve in time at all. Each spatial slice of spacetime, rather, exists kind of on its own. The reason for this goes back to what I said earlier. Global time is neither observable in general relativity nor does it actually mean anything. It is merely a label. Hence, in our quantum version, time vanishes, and rightly so, because if it did appear, then it would break the general covariance of general relativity and imply that we can't arbitrarily change our time coordinate to whatever we want. The Wheeler-DeWitt equation, therefore, presents the universe to us as a quantum movie reel, where each point in time is simply a projection of the global quantum block universe onto a particular coordinate label in our chosen coordinates, which we euphemistically call time. There is no evolution at all. We are all just frozen in 4D amber. Most physicists see the lack of time in the Wheeler-DeWitt as a major flaw in the equation. But DeWitt believed that the equation simply implied that each moment in time was a special case of a different universe. He was, after all, the man most responsible for the many-world interpretation of quantum mechanics. David Deutsch, another proponent of the many-world interpretation, said that human beings aren't even aware that we are used to thinking that different times are special cases of other universes. When you make an economic decision, you're used to the fact that something you buy, some goods, have a different value in different universes. That is, at different times. Even to the same you. You might be slightly different, but even if you aren't very different, the value to you of something might be very different today from tomorrow. For example, oxygen, if you've got COVID, would be differently valuable. Most things change their value gradually over time. You change yourself gradually over time. It's exactly the same in different universes. In different universes, you value different things. In some universes, you're so different that it's not worth calling you you anymore, just like over time it might not be. Although I remember being 15 once, I am not the same person I was then. I have different beliefs and a different understanding. One interpretation of this, the classical interpretation, is that I have evolved in a continuous way from that person to the person I am now. But another idea is that the person I am now is not the same at all, but lives in a different universe. This is enforced by the Wheeler-DeWitt equation, which suggests that although different spatial slices of the universe are related probabilistically, there is no real causal connection between them. That is an illusion. To paraphrase DeWitt, nothing happens in the Wheeler-DeWitt equation. The challenge, however, that this equation does not solve is how to recover the time we all know and love from a timeless equation. Hence, again, some of the attempts to do so from the interaction between a system and a clock, both of which are part of the same unchanging global state that the Wheeler-DeWitt implies. An alternative, which I have argued in favor of, is to rewrite the Wheeler-DeWitt in one higher dimension. In this case, time appears within it like all the other dimensions. The 5D universe is then made up of many related but unconnected space-time slices that contain all 4 dimensions, 3 space, and 1 time. All of these exist in a special kind of space called anti-de Sitter space, which is holographically projected from a 4D boundary. Thus, every slice is independently projected from the boundary, and corresponds to a different energy scale within the boundary quantum field theory. This is based on the well-known anti-de Sitter quantum field theory, ADS CFT correspondence. Just as the energy scales are like separate universes from one another, so the space-time slices are like separate universes as well. Regardless of which interpretation is correct, it is hard to account for our psychological experience of time from a physics perspective. Why does it seem like we live our lives moving forward through time? Is that simply an illusion, with each moment being like a separate you living in a separate universe? Or is it that your mind is somehow independent of the universe and is experiencing reality one moment at a time? Even if equations like the Wheeler-DeWitt are timeless, our minds may, like the system interacting with the clock, gain their sense of time by interacting with clock-like processes. Entropy causes our memories to form in a single direction in time, giving a sense not only that time exists but that we are moving in a single direction. Moreover, neuroscience shows that our brains don't really experience a flow of time at all. What we perceive as a flow is really the internal stitching together of many discrete events and moments. Thus, we only experience the passage of time in retrospect, looking back on the past. In the short term, perhaps 10s of milliseconds, and longer term, minutes, hours, days, weeks, months, and years. This is why the longer back you look in your memory, the faster it seems like time has passed. Most of the moments are missing, and only discrete events remain, counting off the time passed while the majority of your life remains dark. While we see the passage of time as very integral to our lives, our perception of it is no different than our perception of anything else, such as a garden or a forest. We see a few plants and trees, and our brains fill in and process the rest unconsciously, and decide what to keep and what to discard. Then we imagine we saw it all when we in fact saw very little. There is a great deal to the concept of time that we don't understand, least of all our experience of it, and if modern physics tells us anything, it is that we will continue to be surprised by how little we really understand.